Okay, now that we have seen how a reasonably complex system could be designed, let's talk about hardware description languages, which are going to play a very important role in the rest of this course. And what exactly are they and what kind of role can we expect them to play is something that we are going to very briefly touch upon over here. We want to basically bridge the gap between a human readable description and a machine interpretable or a machine understandable description of a circuit or a system, right? And as part of this, what people have done is they came up with, they essentially borrowed analogies from programming languages and said, look, why not use text-based descriptions, but in a very formally specified manner, something which looks like a program essentially, right? Because a program is a very well-defined sequence of steps that tells us how to solve a particular problem, right? There are two important components that come up when you write programs. The first, of course, is the syntax, which basically tells you the structure of the program. For example, in a C program, the syntax basically tells you where you are allowed to put curly brackets and close curly brackets, where you are allowed to define functions, where you are allowed to define variables, right? What the syntax of a function call should look like, right? So you can't just arbitrarily type anything you want and expect it to be a valid C program. It needs to follow certain kinds of structure. Once it is syntactically correct, at least it can be parsed, meaning that it can be read by a compiler and converted into some kind of intermediate format that a computer already is now halfway to understanding in some sense. But then comes the semantics, the actual meaning of each of those statements. So for example, when I do x is equal to 3 plus 5, it logically is telling the compiler that I need to take two constant values 3 and 5, add them together and assign that value into a variable called x, which presumably is going to be used somewhere else. Okay. Now the syntax does not directly tell you anything about that, it only tells you that x is equal to 3 plus 5 is a syntactically valid statement, it does not tell you actually what it means. The semantics, the interpretation of the language is what conveys that to you, right. So if what we would like is to have some way of imposing the same syntax and semantics onto a way of describing hardware, right. But one important thing to keep in mind, which I am going to be stressing upon again and again, is that hardware basically consists of designs, systems that are being built, as opposed to programs that are going to run on a well-defined execution model. There are a lot of subtle differences between these two, which come up as we go further. The important thing that you should keep in mind all the time is you are not writing a program in Verilog. You are never writing a program in Verilog, right? You are designing a module in Verilog and you are maybe writing Verilog code in order to verify that or simulate it and test it and finally hopefully get something working hardware out of it, right? You are not writing a program in the same sense that you would be writing a program in something like C, and that mental model is important to keep in mind as you proceed through the course. Okay, so what are HDLs? They are hardware description languages. That's what HDL stands for, right? And as the name suggests, they are used to describe the functionality of hardware. Okay. The primary purpose of HDLs from the start was simulation, right? Meaning that once you have described what is the expected behavior of a module, you want to in some sense be able to simulate it and see whether, can I apply tests to it and see how it behaves under those test conditions, which basically does not necessarily correspond to hardware. In particular, HDLs do not guarantee anything about actual hardware implementation, right? And they do not specify how the actual hardware is going to get implemented. An example was from the previous case of the 16-bit counter. In general, in the HDL, there are very simple ways of writing a counter code. It does not actually tell you whether you are going to use D-type flip-flops or whether you are going to use a Johnson counter or a Ripple counter or a counter which basically consists of a set of registers with an adder, right? There are many different ways of implementing it. In general, the HDL does not go down to that level of specification, right? Those are choices that are later made by the implementation tools. Verilog and its sort of successor system Verilog are the two most very common languages. I am going to treat them collectively as Verilog, although for a large part what we will be dealing with may actually use certain syntactic constructs from system Verilog in this course. Right. The other sort of most popular HDL is VHDL, which basically stands for very high speed integrated circuit. So, the V stands for very high speed integrated circuit, HDL, right, hardware description language. Now, VHDL tends to be a bit more verbose and it's primarily finds a lot of use in defense and military contexts and sometimes in aviation, and it's found more in Europe, whereas Verilog is more popular in the US and also in commercial designs in general. Okay. The important thing I want to sort of reiterate over here is we will be using Verilog or maybe a subset of system Verilog for most part of this course, but at no point do I want to see that as specifying that that's a better language in some way. It's just that that happens to be things that we are more familiar with and we have the environment for testing over here, right. But for all practical purposes the languages are equivalent, and if you are comfortable with Verilog you should also be able to translate that level of comfort into understanding VHDL code. So, there are a couple of key concepts that you need to keep in mind. One is of so called concurrency, the notion that multiple things can potentially happen at the same time. Whether they do happen at the same time is not exactly the same thing, but at least they do not have dependencies, they do not depend on each other. Concurrency is a slightly subtle concept. Many people confuse it with things running in parallel. It is not necessarily parallel, although in general it's very closely related, right. But concurrency is a very key differentiator of Verilog from other languages like C that you are probably more familiar with. And of course there is also the notion of time, right. There is an explicit notion of time passing in a Verilog or VHDL design, which for example a C program does not have, right. So, once again to repeat, what you are doing is writing modules in Verilog or creating modules in Verilog. These are not programs. There are a few high level concepts that I am just going to brush upon over here, but for the most part we will be going into much deeper study of Verilog in subsequent weeks, right. So, this can just be seen as a sort of flavor of the language. If you are writing a program in C, you might for example see something like this: A is equal to 5, B is equal to A, and yes, what it means is take the value 5, put it into a placeholder corresponding to maybe a memory location or a register corresponding to the name A. Then take that value A and put it into another memory location or register corresponding to a value B. Well defined semantics, this is clearly one happens after the other. I could have a similar looking statement in Verilog where I have two assignment statements, assign A equal to 5, B equal to A, and the interesting thing is this actually has a very important yet subtle difference from the C equivalent. What it says is this A equal to 5 and B equal to A, technically they happen in any order. It could happen that the B equal to A happens first and then the A equal to 5 happens after that. That is what concurrency means. I cannot specify which happens first, right. Now, what will actually happen in practice is that even if I say that the B equal to A happens first, after that I do A equal to 5, that in turn triggers some kind of an update which says okay, later on I am going to go back and say okay, A changed, so I need to go back and once again update the value of B. So, eventually I might end up with the same kind of behavior as what I saw on the left hand side, but the way this gets evaluated in a Verilog simulation is actually quite different and is something to keep in mind. The order of execution in Verilog is not specified, right, and if you sort of depend on something happening in a specific order of this sort for your simulation to work, it is likely to get you into trouble when you actually synthesize something and build a final circuit. The sort of consequence of this is that we can think in terms of so called events, right. Assign A equal to 5, what it is doing is it is taking a value and putting it into a placeholder, right. I am calling this a placeholder rather than a memory location or a register because in practice it is probably not a memory location or a register, it is just a set of wires somewhere in a circuit, right. But what happens is this assignment statement is essentially going to generate an event. There was a change in a value, right, and that change in a value is what I call an event. And what we say is, now the moment there is an event associated with A, I need to go and look at every place that A appears on the right hand side of an equation and say maybe this needs to be updated. I need to recalculate what's there on the left hand side of that equation, right. So event driven evaluation, something that basically allows you to propagate the changes in a systematic manner, is one of the key concepts that we use when we are actually evaluating modules written in Verilog. There are a few different ways by which we can model hardware in Verilog, right, and again I am going to be sort of throwing out a few terms over here. These are things that you will need to sort of absorb through a number of different examples as we move forward, but for now the idea is to basically give you a high level overview of what they are. The first is so-called structural modeling, right, and what we are saying is, let's say that I wanted to implement this particular computation, right. What does it do doesn't matter. I don't know what A, B or C are, and I don't know what Y is used for, but I know that I can basically build up the circuit in this way. So this is a case where I have already decided that my circuit should look like this. I need AND gate, inverter, OR gate in order to create the final output, right. And what we can say is that in Verilog, I could, for example, write it out like this. I would actually write the code, and this U0 is just a name, right. It basically is a name that I am assigning to this particular module, right, or this particular instance of the module, and it's just an identifier, right. The interesting thing is I could have another AND gate somewhere in my circuit, and that would be given a different identifier. I cannot use the same identifier for two different AND gates in the circuit. They need to be called two different things because physically they correspond to two different AND gates, right. What this says is, I have an AND gate which I am calling U0, but the name doesn't matter in this case, which takes two inputs A and B and creates an output T1. T1 is a name I gave to this wire. I also have an inverter, a NOT gate, which I call U1, which takes the input C and creates T2 as an output. And finally I have an OR gate which takes T1 and T2 as inputs and creates Y as the output, right. A very important thing to keep in mind over here is, even though this looks very superficially as though you are calling functions or calling AND gates in a C-like program, these are not function calls, right. What this corresponds to is separate instances of the AND gate, the NOT gate and the OR gate, and the better analogy rather than thinking in terms of function calls is to say these are like chips on a breadboard, right. I am actually taking an AND gate and putting it somewhere on a breadboard. I am taking an inverter and putting it on the breadboard. I am taking an OR gate, putting it on a breadboard, and I am connecting up all the wires as needed. And once I have that, any time A, B or C change, automatically without having to call any functions or do anything else, the AND gate output will get updated, the NOT gate output will get updated. That in turn will generate an event which will cause the OR gate output also to get updated. Okay. So this is structural modeling, where we literally decide this is the final structure that I want and just place the components that I need and connect them up. Another form of modeling is what's called data flow modeling. In data flow, I would have written the same code as something like this. I would basically now just say assign T1 equals A and B, right. So I am not sort of instantiating an AND gate, I am just using the expression out here. Assign T2 equal to not C and assign Y equal to T1 or T2. The same functionality as the previous case, right, but now sort of separated out into three different assign statements, continuous assignments as they are called, where the way that I look at it is A, B, C, anything that happens on the right hand side or RHS of an equation is an input, and anytime there are changes in those inputs, there is an event that gets generated, which in turn causes a flow of information through that particular expression, which in turn could update T1, that in turn generates another input, which in turn is going to trigger this expression out here and possibly create an update in Y. So there is sort of natural flow of information through the system when we do something like this, right? It normally results in fairly simple, rather it can be used when we are trying to model fairly simple expressions, but when we try modeling more complicated kind of expressions, especially things which have multiple conditional statements or a large number of input variables, the data flow modeling can get quite cumbersome. That takes us to the third form, which is essentially where the real power of the languages comes in, which is so-called behavioral modeling. What happens in behavioral modeling is I am now creating something that I call an always block. Now an always block can be thought of as a separate chip of its own on a breadboard if you want to, right? You can almost think of an always block as a module by itself, which takes in certain inputs, performs certain computations and has a large number of outputs possibly, right? It's in general always possible to take out always blocks and create separate modules corresponding to each one of them, although it becomes a little bit clumsy after a while. It basically means that your code becomes too many variables or too many signals being passed around between different modules. You lose the power of the behavioral description that we would like to see, right? What happens over here is I have now defined something that I call a sensitivity list, and what this says is anytime A or B or C, whenever there is any change in any of those values, evaluate everything that happens in here. And what happens to that evaluation is I now go step by step, and this is an interesting variation which basically says I now need to go step by step through the always block statements and update each and every one of these computations. The final result is, if any one of A or B or C changes, I will go back and re-evaluate A XOR B XOR C, assign that value to the variable S, compute this A B or B C or C A and assign that to the value C out, and wait. Any other change that happens in either A or B or C, immediately all of this happens once again. No function calls, this is all event driven. The moment there is a change somewhere, that propagates and causes things to get updated. Right? So this behavioral modeling can be used in order to model really complex behavior, because now you can have fairly large sensitivity lists, you can have fairly large amounts of logic being expressed inside an always block, and that logic can be complex. It can basically involve multiple conditional statements. It can look at the values of, it can create sort of temporary computations and then use those in order to decide whether or not some other thing needs to happen. You can use things like switch case statements in order to do really complex large multiplexers in some sense, right? Or state machine implementations. So always blocks or this kind of behavioral modeling is probably where the real power of the language lies, especially if you are trying to do large scale design. The way to think about it, and you are probably familiar with the term RTL or register transfer level, is you should not think of these as programs that you are writing. You need to think of them literally as, I have a certain hardware that I have in mind. Like for the counter, I knew what I wanted. I knew that there should be a counter, I knew it should have an enable signal, a up down count signal and so on. And the rest of it was basically deciding how do I get that functionality. That functionality is basically saying I can think in terms of registers, which is the present state of the counter, and how they sort of transfer from one place to another. I have a computation being performed based on the output of the register, either count up or count down or hold the last value or load a new value, and that gets transferred back into the counter, right? So that's a register transfer. I could have other kinds of register transfers where I might have, for example, a register file in a CPU where I take two outputs of the register file, perform a computation and then transfer the result back into another register. Each of those kinds of expressions or computations, the way that they are described, that is what constitutes RTL or register transfer level. We are breaking our entire design down into simple modules or simple blocks that constitute moving data around between registers. Why this is important is, you should always keep in mind that your goal over here is not just to write functions or similar code that somehow passes a test bench. You are actually trying to create hardware or model hardware, which means that you need to have the end goal in mind. What should your hardware look like? and then write your Verilog modules to achieve that functionality, right? And once you do that, automatically what you get out of it is basically RTL. You are not really, you don't have to think more in terms of is this RTL or is this the right way of doing it. It will be RTL, it will be synthesizable, it will give you hardware because you started with the mental model of hardware in the first place. Now, we talked about 3 different styles of modeling hardware in Verilog. A couple of more things to be mentioned. One is the fact that sequential elements can exist, right? How do I model sequential elements? So far even the always block was basically talking about a combinational update. Once again we make use of the fact that we can now have events associated with edges, right? We can define a new kind of event. In Verilog we use the notion of something called a pos edge or neg edge in order to detect the edge of a signal, presumably a clock. Similarly, in at least recent sufficiently modern versions of VHDL, there is something called the rising edge of a clock or an equivalent signal that can be used in order to create an event corresponding to a change in a particular signal. Once you know how to detect an edge, it basically means that you are done. You basically have already got the behavioral model required in order to implement a clock, right? And everything else sort of falls in place at that point. One potentially confusing aspect that comes in over here is this notion of non-blocking assignments, which is somewhat Verilog specific. Once again, this is something that hopefully should become clear as you look at more examples, right? The example over here basically shows that in Verilog, according to the syntax, I could write an always block in 2 ways. For example, I have S1 equal to D, S2 equal to S1, S3 equal to S2. Or I could write the same thing with S1 less than or equal to D, S1 less than or equal to S1, or S2 less than equal to S1, S3 less than equal to S2. Less than equal to actually means assigned, right? So, but yeah, how you pronounce it is not very clear. Now the question becomes what goes in here in the always block, right? And the point is, even if we assume that this part has been written correctly, these two, even though they look superficially the same, actually have very different meanings. What this left hand side means is it would basically go through and do it like what a C program would do. It would basically take the value D, put it into S1, take that value of S1, put that into S2, take that value of S2 and put that into S3. So in other words, S1, S2, S3 will all become equal to D. Usually that's not what we want over here. What we want instead is that S1 takes the value of D, S2 takes whatever was previously in S1 before it changed to D, and S3 takes whatever was previously in S2 before it changed to S1. This is exactly what a set of registers does, right, at a clock edge, and this is what we mean by, for example, a shift register in hardware. So this kind of notation where I have the less than equal sign is what's called a non-blocking assignment. It basically performs the assignment but doesn't wait until the assignment is completed before moving to the next stage, right? In practice, it turns out that in most cases this actually ends up being a little bit confusing. It's one of the more confusing aspects of Verilog. So usually the suggestion is follow this rule of thumb. If you are trying to model combinational logic, you should almost certainly be using blocking assignments. If you are trying to model sequential logic, you should almost certainly be using non-blocking assignments. So the question comes, why did Verilog even have this kind of confusion in the first place? And there you need to go back to the HDL, hardware description language, right? When you are trying to describe sufficiently large and complex systems, it is possible that non-blocking assignments can make sense because you are not always talking about combinational or sequential logic. You might be talking about some kind of behavior which has nothing to do with actual hardware, but is just something you want to model in order to simulate the potential behavior of an event-driven system, right? That's where non-blocking and blocking assignments actually start to make sense. When you are trying to actually design hardware, for the most part, this rule of thumb is sufficient and is probably something that you should stick to in all cases. Alright, so now we know the basics of how to write a little bit of Verilog. What do we do with that? We basically want to simulate it, right? And the simulation essentially takes that each component in the design, which could be continuous assignment statements, it could be structural instances, or it could be behavior, the always blocks, and it goes through those and basically interprets what they are supposed to do, right? So for example, continuous assignments are reasonably easy to understand. I look at the right hand side, I compute something and I update it on the left hand side. Behavioral logic also I could go through, but the important thing is I now need to know when should I evaluate the behavioral logic. Remember that these are not functions that are called once and just exit. The idea is the whole evaluation that we are talking about over here happens in an event driven manner. Anytime I have something on the right hand side, the dependencies being changed, I need to go and re-evaluate. If it's one of the inputs to a structural instance, I need to go inside the structural instance and resolve the computations over there. If it's part of the sensitivity list of an always block, I need to evaluate the always block, update it, look at what changed and see what else gets triggered as a result of this computation that I just did. If it's on the right hand side of a continuous assignment, I update that assignment, then again look at the left hand side and see where else does that appear on the right hand side or in a sensitivity list or in a port list of a module instance, re-evaluate all of those until finally things have settled down. Potentially it is possible to create infinite loops over here by not writing code correctly, but as long as you are careful about how you write your design and how you create it, that should never be a scenario that you encounter. Now the exact behavior of each of these pieces of language is defined by the so-called LRM, the language reference manual, right? The semantics, in other words, what is the meaning of each of those statements is what is specified out here, and how to interpret it, how to sort of go about modeling it, how to go about simulating it and so on. What we will be doing is looking at a number of examples and basically learning from examples in terms of how certain things behave. Now we talked earlier about test benches. The interesting thing is Verilog can itself be used to test Verilog code, right? So you can write your test bench also in the same language, right, which is nice. It basically allows you to use the same kind of constructs, it allows you to have assignment statements, structural instances. In particular, what usually happens in a test bench is you create one instance of the design under test or the DUT, right, and then apply inputs to it, and those inputs are the ones that are being changed inside your test bench. It is possible that we could interact with other languages. For example, there are things like the VPI, I think the Verilog procedural interface, which allows you to interact with other languages. You could write C programs, for example, in order to directly change the value of a Verilog signal. So you could perform more complex computations in another language that is more suited for that and pass those values into your Verilog test bench. It's possible, it's not very straightforward. There are tools that sort of make certain things easier or more difficult, well, generally not more difficult, but certain things easier at least, right. Now as part of this, one of the things that we will be repeatedly talking about is this notion of a so-called self-checking test bench. The idea of a self-checking test bench is that for any test bench, for any set of inputs, we know in advance what the expected outputs are. For example, if I am trying to create an adder, then I know that the output for a given set of inputs should be the sum of those inputs. We can store those outputs either in a file or in some way that is accessible to the test bench and perform the comparison of the outputs versus the expected outputs in the test bench itself, so that the test bench finally just outputs a very simple sort of pass-fail kind of information, right. You could also do this by dumping out all the variables and then having a separate script that then goes through those variables and checks whether the output was as expected, but it's usually easier and cleaner to have the test bench itself sort of do the checking for you and tell you whether you passed or failed, right. So self-checking test benches will be something that we use fairly extensively throughout the course and are in general a nice way of sort of writing your test benches. Okay, so we talked about simulation, right, but simulation is only part of the story. Essentially what it says is I have now got my requirements, I have got my detailed requirements, I have written some code which basically corresponds to a set of Verilog modules which hopefully models the hardware that I am trying to design, and the simulation is sort of putting that in a test bench and saying, okay, if I apply these inputs, this is how I expect my module to behave. So far so good, everything looks okay, right, but that's not real hardware, that's just a model of the hardware. So what do? We can then go from there and say, okay, how do I convert this program into actual hardware, And this process is very similar to the idea of software compilation. We first parse the program, break it up into some kind of an intermediate representation, perform optimizations on it, and whereas in a normal software compiler like a C compiler, I would have a code generation step which would finally generate machine instructions, right, assembly language or machine instructions that will actually run on my processor. Here what I am going to do is actually generate an output for a target, right, and that target could be a set of gates which needs to fit on an FPGA or is a custom circuit to be built in a on silicon, or could be a set of chips that I need to select and finally put together on a breadboard. Okay. This process at a very high level is mostly pattern driven. So for example, if I see if statements, it is more or less going to create a mux, right. If I see an at passage clock, then it's going to infer a flip flop, right. So those kind of things are things to keep in mind. It's not as though the compiler has some kind of magical way of understanding what you are trying to do. It's sort of looking for patterns and saying, okay, this corresponds to a flip flop, this corresponds to a mux, this corresponds to a counter. Let's put all of this together and see if it makes sense, right. But that is the process of synthesis, and if your code has been well written and your modules have been well designed, and if they passed simulation and if they pass through synthesis, hopefully the final set of gates that you get will also be able to pass the same simulation, since after all we can model the same gates in simulation in Verilog itself, and when you finally build the circuit out of it, they should behave as expected. The important point is the language by itself does not guarantee any of these steps, right. It pretty much says, okay, yeah, there are certain ways, if you have written your code properly and not tried to do some kind of strange use of the language that it does not normally support, you should in most cases end up with a scenario where everything synthesizes properly and works as expected, but it does not guarantee that unless you have followed the procedures properly. So I mentioned the word synthesis target, right. Like I said, you could also target something like, discrete chips to be put on a breadboard, but in practice you usually use things like Verilog for designing circuits at a fairly large scale. And at that point what we are usually doing is maybe targeting a set of standard cells that have been provided in order to build what are called ASICs, application specific integrated circuits, right. And these standard cells, right, which could be AND gates, OR gates, but they could also be AND gates of different sizes, right. Even a NOT gate, an inverter, you will find that in a standard cell library there are probably 3 or 4 different variations of inverters. Why? After all, they all perform the same logical function, but that's where reality kicks in and we find that there are actually delays associated with gates, there is power consumption, there is area, and all of those factors need to be taken into account, and because of that we provide multiple different variants of the same gate that occupy different amounts of area, that have different speeds, different power consumption, and finally end up giving you different final costs for the design that you are trying to make. Okay. Now these cells are typically foundry dependent. Many of you may have heard of the company TSMC, Taiwan Semiconductor Manufacturing Corporation, at this point in time the largest manufacturer of ICs in the world. There are others, UMC, there is Global Foundries, and some companies like Intel and Texas Instruments have their own foundries as well, usually for more specialized kind of chips. The foundry is like a factory. It's basically where the silicon actually gets converted into a set of chips, and building a large foundry in general is an extremely cost intensive process, right. So the standard cells are usually provided by the foundries. They are dependent on which foundry, right, which cells you have available to you are dependent on the foundry that you are working with, and based on that you could then choose that as your synthesis target. The other option is the so-called FPGA, the reprogrammable hardware, that we will be talking a lot more about later. In both these cases, instead of generating executable code or machine code that runs as instructions in a processor, what we are going to do is generate a netlist, that is to say a set of gates and the connections between those gates. That's called a netlist, right. So in some sense that's all, right? The difference between compiling to software versus compiling to hardware is just the final target, and a lot of the intermediate steps actually remain the same or very similar.